Okay, we'll start now. So is my screen visible to all of you?
Yes, sir.
Okay, good. So we had discussed about infinitesimally small rotation. Okay, and that from that actually we got that the generator is basically angular momentum. If we have a rotation phi z, then the generator will be Lz. So similarly, if you have phi x, it will be Lx, and if you sorry, uh, if we have phi y, it will be Ly. And in that process, we also understood that if we take Lx, Ly commutator, that will be equal to IH cross Lz. Yeah, Z. Okay. So that is the commutation relation, and that we also have discussed that will be cyclic. Lx Ly will give Lz, Ly Lz will give Lx, and Lz Lx will give Ly. Now, next step is basically to talk about finite finite rotation in terms of infinitesimal small rotation. Okay, so finite rotation is basically large number of infinitesimally small rotations, isn't it? So how exactly? Let's say we have our finite rotation is phi z. Let's say our finite rotation is phi z. If we divide n number of n number of infinitesimal small rotations, then each rotation, each infinitesimally small rotation, that is equal to phi, oh sorry, phi z by n. So this is our infinitesimal small rotation. And for a large number of rotation, we'll have n goes to infinity. So the rotation operator Rz of phi z, this can be written as limit n going to infinity identity minus I phi z Lz by n h cross. So this part is basically, if you remember, earlier we used to have I identity minus I phi Lz by h cross. Now phi is kind of replaced here. Phi is replaced by phi z by n, because this phi z by n is the infinitesimally small rotation. And this expression can be written as exponential minus I phi z Lz by h cross. So similarly, if this is like our Rz phi z, similarly if we have Rx phi x, it will be exponential minus I phi x Lx by h cross, and Ry phi y will be equal to exponential phi y Ly by x. Okay. So if we want to write in general, the generalization. So what exactly we will write? Rn phi, n is the direction, would be equal to exponential minus I phi L dot n cap by h cross. Or if we explicitly write it, it will be equal to exponential minus I phi Lx nx plus Ly ny plus Lz nz by h cross. All right. Where nx, ny, and z are the components of the n vector along x, y, z axis. Okay. So what is it? The important part is what we need to understand over here, that this expression, components of the angular momentum, okay, that cannot be expressed as one after another. ଆମେ କଣ କହୁଥିଲେ ଯେ ପ୍ରଥମେ ଯୋଉଟା ଆମେ କମ୍ୟୁଟେସନ ରିଲେସନ ରେ ବି କହିଛୁ, ଟ୍ରାନ୍ସଲେସନ ବେଳେ ଗୋଟେ କଥା ଥିଲା ଯେ ଯଦି ଆମେ x axis ରେ ମୁଭ୍ କଲୁ ତାପରେ y axis ରେ ମୁଭ୍ କଲୁ, ଆମେ ଯୋଉଠି ପହଞ୍ଚିବୁ, y axis ରେ ମୁଭ୍ କରିକି x axis ରେ ସେତିକି ମୁଭ୍ କଲେ ଆମେ ବି ସେମ୍ ପଏଣ୍ଟ ରେ ପହଞ୍ଚିବୁ। କିନ୍ତୁ ରୋଟେସନ ରେ ସେୟା ହବନି। ଯଦି ଆମେ ଫାଷ୍ଟ ୱିଥ ରେସ୍ପେକ୍ଟ ଟୁ x axis ରୋଟେଟ୍ କଲୁ, ତାପରେ ୱିଥ ରେସ୍ପେକ୍ଟ ଟୁ y axis ରୋଟେଟ୍ କଲୁ, ଯୋଉଠି ପହଞ୍ଚିବା, ପ୍ରଥମେ y axis ରେ ରୋଟେଟ୍ କରିକି ତାପରେ x axis ରେ ରୋଟେଟ୍ କଲେ ନଟ୍ ନେସେସରି ସବୁବେଳେ ଆମେ ସେମ୍ ପଏଣ୍ଟ ରେ ପହଞ୍ଚିବୁ। Okay, so that is why let me write down over here. So exponential minus I phi Lx nx plus Ly ny plus Lz nz, what you do bracket by h cross is not equal to exponential minus I by Lx nx by h cross into exponential minus I by Ly ny by h cross into exponential minus I by Lz nz. What is the reason? H, angular momentum operators do not commute. Yes, angular momentum operators do not commute. Okay. Is it clear up to this point? Am I audible?
Yes, sir. Yes, sir.
Yes. Okay. Good. Good. All right. Next is uh, I guess this already has been taught in quantum mechanics 1. Uh, J, total angular momentum, is equal to L plus S. এই কথাটা পড়ে হয়েছি quantum mechanics 1 রে,
Yes, sir.
right? So this is your total angular momentum. Hmm. This is orbital. Wait. Orbital angular momentum, and this is spin angular momentum, right? Now, what exactly in quantum mechanics we have this J operator that is equal to L operator plus S operator, S operator. Now, all of us know this, whatever we are phi x, phi y, phi z, we are talking, this is basically relating to orbital angular momentum. But then we also have spin, because whatever system we are applying, these are basically electrons, so they have spin. So, total effect, what we will see in a quantum mechanical measurement is basically the total angular momentum. We will not see L. Actually, we will not see L. Rather, we will see the effect. We'll see the effect of J. So, if we write in terms of J, these operators, rotation operators, how exactly we will write? So, your Rx phi x will be equal to identity minus I phi x. In terms of instead of Lx, what we will write? Jx by h cross. Similarly, Ry phi y will be equal to identity minus I phi y jy by h cross. Rz phi z will be equal to identity minus I phi z jz by h cross. Okay. All right. And similarly, for finite rotation, in terms of whatever we have written, uh, this is for infinitesimally small rotation. For finite rotation, so these three basically for infinitesimally small rotation, and for finite rotation, what we will write will be Rx phi x will be equal to exponential, what is it? Minus I, then phi x, L epsilon, Jx whole sorry, Jx. Just a second. Jx by H cross. And similarly, Ry Iy and Rz by Z is equal to exponential minus psi by Z Jz by H. All right, this is what we will get. Coming back to your uh, material, yeah, this we already discussed. Yeah, over here. So, what is it? Yeah, this is what we already have discussed. In this part. This one, and this one, Jy and Z. All right, this we already have discussed. Next, it is telling rotation of an observable. Initially, we were talking about rotation of the system and rotation of the wave function or the state function under rotation. Now, rotation of an observable. ଆମେ ଯୋଉ ଗୋଟେ କ୍ୱାଣ୍ଟିଟି କୁ ପୋଜିସନ ହେଲା ମୋମେଣ୍ଟମ ହେଲା ଏନର୍ଜି ହେଲା ସେଇଟା ରୋଟେସନ ରେ କଣ ଚେଞ୍ଜ ହବ so that's what it is telling the consider an operator O which describes an observable O of the physical system then let phi 1 phi 2 phi n cats be the eigenkets corresponding to the discrete non-degenerate eigenvalues of O eigenvalue equation पढ़ा है आइगेन वैल्यू ମାନେ କଣ ତମେ ଗୋଟେ ସପୋଜ ତମେ ଗୋଟେ ଅପରେଟର ନେଲ ଏନର୍ଜି ଅପରେଟର ଓକେ let us say you took an energy operator let me explain little bit then I will come back to this part suppose you take an operator energy operator kiya all of you know what is the energy operator Hamiltonian right h this is basically p square by 2m plus br or bx whatever right isn't it now if you want to get the energy of a system, then what you have to solve is H psi is equal to E psi, or rather H psi n is equal to E n psi n, where this psi n's are eigenstates. Eigenstates of what? Of energy eigenstates. And they are orthogonal to each other, right? Psi 1, psi 2 would be equal to 0. And psi n mod square will be equal to 1. So that's what the property of state functions we have discussed. So based on that, now here it is telling that suppose you have an operator O which describes the observable O of the physical system, and phi 1, phi 2 up to phi n kets are the eigenkets corresponding to the discrete non-degenerate eigenvalues of O. So the equation they will satisfy is O cap phi I will be equal to AI phi I, just like H psi is equal to E psi. So here this is the eigenstate, eigenvalue equation. Any arbitrary state of the system can be written as a superposition of the eigenkets of the O. Just like any wave function psi, you already have studied this. Huh? Any wave function, let me write it. If you have take any wave function psi, that will basically be equal to summation over I ci psi I, where the psi I are basically the energy eigenstates of the Hamiltonian. ତେଣୁ ତମେ ଯେକୌଣସି ଗୋଟେ ଷ୍ଟେଟ୍ ନେଲେ କ୍ଲୋଜର ରିଲେସନ ତମେ ପଢିଛ, ଯଦି ତମେ ସାଇ ୱାନ୍ ସାଇ ଟୁ ଦିଟା ଷ୍ଟେଟ୍ ବେସିସ୍ ଷ୍ଟେଟ୍ ହେଲା, ତାହେଲେ ତାର linear combination C1 psi 1 plus C2 psi 2 will also be a solution. So similarly, any state function psi can be expressed as a linear combination of all the eigenstates. That's what it is telling, that any arbitrary state of the system can be written as a superposition of the eigenstates. All right, I'll take a pause here. I'll take some water and then I'll come back. Okay, just a couple of minutes. Okay, let us start again. So phi O phi I is equal to AI phi I. We now want to find how the observable is affected by the rotation of the physical system. ଯଦି physical system ଟା rotate ହେଲା ତାହେଲେ observable ର କଣ ହବ? So let us now suppose that the system is in its eigenstate phi I. System ଟା କୋଉଥିରେ ଅଛି? Phi I eigenstate ରେ ଅଛି. If we measure the observable O using some measuring device, we would get the value AI. Let us now assume that both the system and the measuring devices are rotated. This is important. We assume that both the system and the measuring devices are rotated. A geometrical rotation described by the matrix R. A geometrical rotation described by the matrix R. Since there is no change in physical system with respect to measuring device ର measurement ଉପରେ କଣ system ଟା change ହବ କି? Change ହବନି ନା। ତମେ ଗୋଟେ rod ର length ଟା ଗୋଟେ tape ନେଇକି measure କଲେ କଣ rod ର length change ହେଇଯିବ? Change ହବନି because of measurement. The result of measurement should still be AI. So phi I R will be basically rotation ହେଲା ପରେ ଯୋଉ state ଟା ଆସିବ ସେଟା କୋଉଥିରେ express କରାଯିବ? Rotation matrix or rotation operator R operating on state phi I. Okay, let me write down. So phi I R representing after rotation. After rotation, this is equal to R operator operating on state phi I. Now what will happen once we have what happens after rotation to the observable? What happens to the observable after rotation? So we'll operate, sorry, O. The operator is O, O operator. But after rotation, OR operating on phi I R will be equal to AI phi I R. This AI will not change. Why it should not change? Why? Because rotation should not change the the value of the observable. Value of the okay. So if I write now in terms of operator R, this equation, if I write in terms of, so that will be O R. Now phi I R will be equal to R phi I is equal to AI R phi I. If we multiply R dagger on both sides, multiplying R dagger on to the left of both sides. Okay, what exactly we will get? R dagger O R phi I is equal to R dagger AI R phi I. Now this is AI is a number and these two are operators. So that's why AI will come outside. So this will become Ri, R dagger, R phi I. But this rotation is unitary operator, right? Rotation is a rotation operator is an unitary operator. This implies R dagger R is equal to identity, right? So what we can write then? R dagger O R operating on phi I will be equal to AI identity phi I. Identity phi I will be equal to AI phi I. Is it? So what does this mean? This right hand side is same as our initial equation. eh? So this can be written as O operating on phi I because eigenvalue equation. Eigenvalue equation we have is O phi I is equal to AI phi I. This is where we started. So A equation to this equation, what we will write? R dagger. So coming from there, R dagger O R phi I is equal to O phi I. Or what we can write? This implies R dagger O R will be equal to O. Okay, isn't it? Oh, I have made one mistake over here. I have left actually. Just to correct from here, phi R it will be O R on the left. O R, this will be O R. So O R. So after rotation, if you want to find, so this implies OR will be equal to what? R O R diagram. ତାମାନେ କଣ ହେଲା ଯଦି ଗୋଟେ ଅବଜରଭେବୁଲ ରୋଟେଟ ହେଲା ତାହେଲେ ତାର ଅପରେଟର ଆମେ କେମିତି ପାଇବା ରୋଟେସନ ଅପରେଟର ଅବଜରଭେବୁଲ ଅପରେଟର ଦେନ୍ ଆର ଡାଇଗ୍ରାମ ଏଇଭଳିଆ କଲେ ଆମେ ରୋଟେଟେଡ ସିଷ୍ଟମ ରେ ଏ OR ର ଭ୍ୟାଲୁ ପାଇପାରିବା ଇଜ ଇଟ କ୍ଲିୟର ଟୁ ଅଲ୍ ଅଫ ୟୁ
सर एक साइड
Yes,
मल्टीप्लाई
sir.
की थी ना एक से डिवाइड केम थिलानी
କୋଉଥିରେ
ତା ଲାଷ୍ଟ ଟା r ଡାଇଗର o କେପ୍ r equals to o କେପ୍ ଥିଲା ଦେନ୍ o କେପ୍ r ଟା
ହଁ
ଯେତେବେଳେ କାଢିଲେ ସେଟା ଡିଭାଇଡ ହେଲାନି
divide hapani. Operator, okay, let me write that. Operators are not divided. So what exactly? Let me rewrite this here. Huh? So then it will be clear. So what you do actually? So you multiply R onto the left, R dagger, O R, R, then R dagger. गोटे R left रे multiply करिवो गोटे R dagger right रे multiply करिवो ताले right side रे कोन हिजबो
हाँ हाँ सर,
R
हाँ सर, मुझे
R dagger. Now this is equal to identity. This
हाँ
is equal
वन
to
है ना,
identity.
हाँ सर,
Okay. So that's why I cap O R I cap is equal to R
इक्वल्स
O
टू
R dagger. So this implies O R is
इन
equal to
इनटू
R
वन।
O R dagger. Okay.
हाँ सर,
Clear? ताले
यस
observable टा केमिति हमें पाइबा rotated system रे हाँ सेटा भी जमा पड़ी गला नहीं कि ताकू जदि हमें infinitesimal rotation or finite rotation express करिबा if we want to express in let's say in terms of infinitesimal rotation eh? infinitesimal rotation তাহলে কোন করিবা rotation matrix টা কেতে মনে পড়ুଛି rotation operator identity minus I phi j dot n right by h
एक्स
cross so that's what our r dagger टा केते होगा ताहले r dagger will be I जगह रे minus I होगा right so I cap plus I complex conjugate टा ना phi j dot n by h cross so your phi sorry or observable operator in a rotated system will be equal to r o r dagger so which will be equal to I phi by h cross o and then I plus I by j dot n so by h cross. This is what this is how we will get our operator or observable in a rotated system. Okay, is this clear up to this point?
Yes, sir.
यस सर,
Yeah. So
Yes,
this is
sir.
what we have. It is done uh, in the material so that you can follow. Huh? All right. Next is so what we have done now till now. One is space translation. Another is rotation. The next part is time translation. If we ମାନେ ଆମେ ଯଦି ଗୋଟେ ସିଷ୍ଟମ ର ଡାଇନାମିକ୍ସ କଥା ଷ୍ଟଡି କରିବା ପାଇଁ ଚାହୁଁଛୁ ଆମେ କଣ କରିପାରିବା ଆମେ ତାକୁ ରୋଟେଟ୍ କରିପାରିବା ଆମେ ତାକୁ ଟ୍ରାନ୍ସଲେଟ କରିପାରିବା ନହେଲେ ୱିଥ ରେସ୍ପେକ୍ଟ ଟୁ ଟାଇମ ଏବେ କଣ ଅଛି 5 ଘଣ୍ଟା ପରେ କଣ ହବ 10 ଘଣ୍ଟା ପରେ କଣ ହବ ସେଇଟା ଜାଣିପାରିବା ଦିସ୍ ଇଜ ବେସିକାଲି ଡାଇନାମିକ୍ସ ରାଇଟ୍ so let us now try to understand what happens in case of a time translation ମାନେ ହେଉଛି t equal to 0 ରେ start ହେଇଥିଲା t equal to t ରେ କଣ ଠିକ ଅଛି so that is what it is referring here in unit 11 of MPH 004 MPH 004 is quantum mechanics right one quantum mechanics one we have already discussed the time evolution operator for a state k time evolution operator ମନେ ପଡୁଛି ନା ମନେ ପଡୁନି ସମସ୍ତଙ୍କର ଟାଇମ ଇଭଲ୍ୟୁସନ ଅପରେଟର ମନେ ପଡୁଛି ନା ମନେ ପଡୁନି ନାଇଁ let me write down something IH cross del psi by del t is equal to h psi এই কথা মনে পড়ছে ନା
हाँ
ଏବେ
हाँ
ଗୋଟେ
sir.
କିଛି ପଢିଥିଲା କଣଟା ସେଟା तापर तुम ये गोटे कहुई तुमको साइ दीटा फंक्शन हो गोटे साइ ऑफ एक्स और गोटे साइ ऑफ टी तेणु ये साइ ऑफ टी टा हूँ टाइम इवोल्यूशन टा तेणु से तुम पाई दिस इज टाइम डिपेंडेंट श्रोडिंगर इक्वेशन तापर ये आसो ये तुमको पढ़ाई टाइम इंडिपेंडेंट श्रोडिंगर इक्वेशन व्हिच इज बेसिकली इक्वल टू SI is equal to ESI where H is equal to V square by 2m plus Vx or Vr whatever है नहीं
हाँ सर
तो इस psi t मतलब डिफरेंट नोटेशन यूज करा जाई पारे psi x ut but basically one is space part one is time part okay dita part करा है space part does not depend on time part does not depend on space mutually orthogonal okay so this is basically your time evolution সেই কথাটা এটি let me come back to the material সেই কথাটা এটি तुमको କୁହାଯାଇଛି that the evolution operator ut ର କାମ କଣ ନା ut ଟା ଯଦି psi 0 ଉପରେ ଅପରେଟ କରିବ ସେ ୱେଭ ଫଙ୍କସନ ଟାକୁ psi t କୁ ନେଇଯିବ ମାନେ ତମେ ଯଦି ୱେଭ ଫଙ୍କସନ ଟା t equal to 0 ରେ ଜାଣିଛ ୱେଭ t equal to ଆଉ ଗୋଟେ ଟାଇମ let's say t ରେ ଜାଣିବା ପାଇଁ ହେଲେ what you have to do you have to operate with ut and what is that ut will be of the form e to the power minus iht by h cross ତମେ ମାନେ ସବୁ ପଢିଥିବ ସେଥିରେ ମୁଁ କାଲି ଟିକେ ଲେଖିଦିଏ e to the power minus I omega t এই কথা পড়িଥିବ so time evolution is like this or this is equal to e to the power minus I h cross omega t by h cross which is basically e to the power minus I e t by h cross e ଟା କୋଉଠୁ ଆସିବ h is equal to e psi ପରା ତେଣୁ e to the power minus I h operator t by h cross ବୁଝିହେଲା ନା ନାଇଁ
हाँ सर बुझला
ସେ କଥା ଏଠି କୁହାଗଲା so psi t state what we, how is that you will get will have ମାନେ ଯଦି t0 ଟା 0 ହେଲା ତାହେଲେ psi 0 ଲେଖାଯିବ ଯଦି t0 ଟା 0 ନ ହେଇକି ଆଉ ଗୋଟେ ଭ୍ୟାଲ୍ୟୁ ହେଲା ତାହେଲେ ଆମେ ଏଇଭଳିଆ ଲେଖିବା utt0 operating on psi t0 okay and if we do that what exactly we will get the time evolution operator will be like this so e to the power minus ih e to the power minus ih t minus t0 by h cross ବର୍ତ୍ତମାନ କଥା ହେଲା ଆମେ ଯେମିତି ଦିଟା ट्रांसलेशन स्पेस ट्रांसलेशन रे पढ़िले आउ रोटेशन रे पढ़िले स्पेस ट्रांसलेशन रे कोन पढ़िले जे जदी हमें विथ रिस्पेक्ट टू एक्स मूव करूछु फर्स्ट तापर सेकंड स्टेप रे विथ रिस्पेक्ट टू वाई मूव करूछु हमें जोठी पहुंचीबु जदी हमें प्रथमे वाई रे मूव करिवु तापर एक्स रे मूव करिवु तने हमें सही जगह रे पहुंचीबु दैट मींस वी कैन साइमल्टेनियसली डिटरमाइन टू पोजीशंस वेयर हमें जेतेबेले रोटेशन कलु सेठी कोन देखिलो ना जदी हमें विथ रिस्पेक्ट टू एक्स रोटेट करूछु फर्स्ट स्टेप रे और सेकंड स्टेप रे विथ रिस्पेक्ट टू वाई रोटेट करूछु हमें जो जगह रे पहुंचीबु प्रथमे विथ रिस्पेक्ट टू वाई रोटेट करी तापर विथ रिस्पेक्ट टू एक्स रोटेट गला हम से जगह रे पहुंची न पार दैट इज व्हाई द कम्यूटेटर्स is not zero commutator bracket of lx and y is not zero rather it is non zero एबे कथा उठुची जे लेट्स से मु प्रथमे टाइम ट्रांसलेशन कली t equal to t0 रे थिली तापर t1 को गली तापर t2 को गली सपोज मोर एई बळे स्केल अछि प्रथमे मु t0 रे थिली तापरे t1 को गली तापरे t2 को गली फर्स्ट स्टेप रे एटा सेकंड स्टेप रे एटा ता माने मु कोन कहि परिबी कि जे मु t1 को जाई कि तापरे t2 को जिबा जहा एका बेले t0 रु t2 को जिबा सैया मो कथा बुझी परछो ना माने
ହଁ
सेटा
ସାର୍
कंसेक्यूटिवली एक्सप्रेस करि परिबी कि नाही ताको देखेबा पई एई मैथमेटिक्स टे करा हैछि सो psi t is taking from t0 to t2 so this is basically taking the system from t0 to t2 ତେଣୁ ଏଇ ଯୋଉ ଅପରେଟର ର ଡେଫିନେସନ ୟୁଜ କରିକି ଆମେ ଲେଖିବା କଣ e to the power minus IH t2 minus t0 by h cross okay now this hamiltonian is independent of time right ତମେ ଯୋଉ hamiltonian conservative system ପଢିଛ h is equal to କେତେ p square by 2m plus v right ଏଥିରେ time ତ ନାହିଁ there is no time in that ତାହେଲେ ଆମ ପାଖରେ କେବଳ ଅଛି ଏଠି କଣ t2 minus t0 ଆକୁ ମୁଁ ଲେଖିପାରିବି କଣ t2 minus t1 plus t1 minus t0 ଗୋଟେ t1 plus କରିକି ଗୋଟେ t1 minus କରିପାରିବି ଠିକ ଅଛି ସେଥିରେ ତ କିଛି ଏକ୍ସପ୍ରେସନ ଟା ଚେଞ୍ଜ ହଉନି ନା ଦିସ୍ ଇଜ ସେମ୍ ରାଇଟ୍ t2 minus t0 ଯାହା t2 minus t1 plus t1 minus t0 ସେମ୍ ଜିନିଷ ତାହେଲେ ମୁଁ ଆକୁ ଲେଖିପାରିବି t2 minus t1 ଗୋଟେ ପ୍ଲସ୍ t1 minus t0 ଆଉ ଗୋଟେ ସେଇ କଥା ହିଁ এই ସ୍ଟେପ ରେ କରାଗଲା t2 minus t0 କୁ ଆମେ ଲେଖିଲେ t2 minus t1 plus t1 minus t0 এই ମାଇନସ ଟାକୁ କାହିଁକି ନା এই ମାଇନସ ଟା ମାଇନସ i ସେଟା କମନ ନିଆ ହେଇଛି ତେଣୁ ମାଇନସ i ଟା ମଲ୍ଟିପ୍ଲାଇ ହେଲେ ତ ମାଇନସ ହିଁ ଦବ ନା so that's why we'll get two expressions e to the power minus ih t2 minus t1 by h cross e to the power minus h t1 minus t0 by h cross which is basically two translation operators so finally what we can conclude that going from t0 to t2 is same as going from t0 to t1 and then t1 to t2 same କଥାଟା ତାମାନେ ଟାଇମ ରେ ସେମ ଯୋଉଟା ଆଇଗେନ ଷ୍ଟେଟ ଗୁଡା ଟାଇମ ରେ ରହିବ ସେଗୁଡାକୁ ଆମେ ସାଇମଲଟେନିୟସଲି ଡିଟରମାଇନ କରିପାରିବା ସେମାନେ କମ୍ୟୁଟ କରିଯିବେ commutator will become equal to 0 okay I'll possibly stop it here next class I'll be talking about the generator for this time translation and then we'll proceed any question up to this point
No, sir.
କାହାର କିଛି question କାହାର ଅଛି କି
नो सर
okay ସବୁ ବୁଝି ହଉଛି ତ
यस सर
Yes, sir.
good good ତମମାନେ ଆକୁ ଟିକେ ଆଗୁଆ ଟିକେ ପଢି ଆସିଥିବ କାରଣ ଆମେ ଟିକେ ଫାଷ୍ଟ ଯିବା କାଲିକି କନଜରଭେସନ ଲସ୍ ଏଇଗୁଡା ଟିକେ ଭଲସେ ବୁଝିଗଲେ ମୁଁ ଭାବୁଛି ନେକ୍ସଟ ବ୍ଲକ୍ସ ଗୁଡା ତମ ପାଇଁ ବୁଝିବା ପାଇଁ ସହଜ ହବ ହେଲା
यस सर
Yeah. If no more question then I will sign out today thanks for your attention
Thank you, sir.
थैंक यू सर सर इम्पोर्टेंट क्वेश्चन देखो लास्ट
ହଁ ମାନେ एक्चुअली इंपोर्टेंट क्वेश्चन ମାନେ ଏଇ ଯୋଉ ତମମାନଙ୍କୁ ସବୁ ସର୍ଟ ଆନ୍ସର ଟାଇପ ଆଉ ପରକୁ ଆସିବ ଲଙ୍ଗ ଆନ୍ସର ଟାଇପ ହେଲା ସେଇଗୁଡା ଟିକେ ଭଲସେ କରିଥା ଆଉ ପ୍ରାୟତଃ ମୁଁ ଯୋଉଗୁଡା ଡେରାଇଭ କରିଦଉଛି ମାନେ ମ୍ୟାଥମେଟିକ୍ସ ଟା କରିଦଉଛି ଟିକେ ସେଗୁଡା ବି ଇମ୍ପୋର୍ଟାଣ୍ଟ ହେଲା ଲେଟର ଅନ୍ ଆକ୍ଚୁଆଲି ଆମେ ପୁରା ପାର୍ଟ ଟା ତ କଭର କରି ମୁଁ ଜାଣିନି କେତେଟା କଭର କରିପାରିବା କିନ୍ତୁ ଭେରିଏସନାଲ ପ୍ରିନ୍ସିପଲ ଯୋଉଟା ଅଛି ଆଗକୁ ଯୋଉଟା ପଢା ହେବ WKB ଆପ୍ରୋକ୍ସିମେସନ ଭେରିଏସନାଲ ପ୍ରିନ୍ସିପଲ, ସେଗୁଡା ଟିକେ ଇମ୍ପୋର୍ଟାଣ୍ଟ, କିନ୍ତୁ ତାକୁ ବୁଝିବା ପାଇଁ ହେଲେ ଏଇ ଜିନିଷ ଗୁଡା ଆଗ ନିହାତି ବୁଝିଥିବା ଦରକାର, ନହେଲେ ତମେ ସେ ମ୍ୟାଥମେଟିକ୍ସ ଟା ବୁଝିପାରିବନି। ଠିକ ଅଛି।
ଓକେ ସାର୍। ହଁ
ସାର୍
ସାର୍।
ଇଗ୍ନୋ ସବୁ 5 ମାର୍କସ୍ ଆଉ 10 ମାର୍କସ୍ ର କ୍ୱେଶ୍ଚିନ୍ ହିଁ ପକଉଛି। ଏ ସବୁ ଲଙ୍ଗ କ୍ୱେଶ୍ଚିନ୍ ଭାରି, ଯାହା ପ୍ରିଭିୟସ୍ ଇୟର ମାନେ ଦେଖିକି
ନାଇଁ ନାଇଁ, ମାନେ କୋଶ୍ଚିନ୍ ଟା 5-10 ଟା ଡିସାଇଡ୍ କେମିତି ହବ? ସେଇଟା ଡିସାଇଡ୍ ହବ ଯେ ମାନେ ଡେରିଭେସନ ଟା କେତେ ଲମ୍ବା ହବ, ସେଇଆ ତ। କିନ୍ତୁ
ଆଜ୍ଞା
ସେଥିରେ ଯୋଉଟା ମାନେ ତାକୁ ବୁଝିବା ପାଇଁ ହେଲେ, ସପୋଜ ଆମେ ଯେମିତି ଦିଆଗଲା ଗୋଟେ କୋଶ୍ଚିନ୍ ଏଠି ଥିଲା, LXLY କମ୍ୟୁଟେଟର will be equal to IH cross LJ। ତାକୁ ଜଣେ ଚାହିଁଲେ 2-3 ଲାଇନରେ ବି କରିଦେଇ ପାରିବ, କିନ୍ତୁ ସେଟା କୋଉ ଭଳିଆ ପଚରା ହେଇଛି, କଣ ୟୁଜ କରିକି ତାକୁ ଏକ୍ସପ୍ଲେନ କରିବା ପାଇଁ କୁହାଯାଇଛି, ସେ ତା ଉପରେ ଡିପେଣ୍ଡ କରିବ। ମୋ କଥା ବୁଝିପାରୁଛୁ? ଏଠି ଯେମିତି କହିଲା
ଆଜ୍ଞା ସାର୍
ୟୁଜ ଦ ପ୍ରପର୍ଟିଜ ଅଫ ଦ ରୋଟେସନ ଅପରେଟର ଟୁ ପ୍ରୁଭ ଦିସ୍ ଥିଙ୍ଗ, ହେଲା। ତାହେଲେ
ଆଜ୍ଞା
ସେଇ ଅନୁସାରେ ସାର ମାର୍କ ଟା ଡିସାଇଡ୍ ହେଇଯିବ। ଠିକ ଅଛି।
ଆଜ୍ଞା
All right, see you tomorrow same time.
ୟେସ୍ ସାର୍।
ଥ୍ୟାଙ୍କ ୟୁ ସାର୍।
Shall we start?
Yes sir.
Okay. Okay. My slide is visible. Hello.
Yes sir. Yes sir.
Okay. So in the last class we discussed about the kinematics of rigid body. Today about the dynamics of rigid body, particularly the rigid body equation of motion and Euler equation and heavy symmetrical top. Okay. So rigid body equation of motion, as you know, dynamics means associated the motion. Here we calculate the kinetic energy, angular momentum, etc. thing. Uh, Particularly okay, here angular momentum and kinetic energy motion about a point. Since is rotation, one is axis of rotation, the body is rotating about an axis. Sometimes we call the origin of axis the rotation around a point. Means we assume that point is the origin of the coordinate axis. The body is rotating around that. So this is a picture. Let us consider the rotation of a body. Actually, this one is short. Here we take this analysis to show that the angular momentum, angular velocity omega. Omega is same if a rigid body is moving. Whatever frame we use to study it, we assume that omega is same. Last time we see the angular velocity omega of the Earth. Similarly, when we apply this, we assume that angular velocity of that rotating system is constant type of thing. Okay. This just show that it's not so important. Omega 1 is equal to omega 2. So we only say that omega is same angular momentum. Now calculate the angular momentum and kinetic energy. From a rigid body, we know that angular momentum is equal to L is equal to R cross P. So if it constitutes a number of particles, then summed over Ri cross Pi. Is not it? Hello?
Yes, sir.
Yes, sir.
But P is mass into velocity, MI/Vi. So I can write this L is equal to summed over I Mi Ri cross Vi. Okay. But we know that dRi by dt is from last class, the rotating body, it equal to dRi by dt rotating or body plus omega cross Ri. Okay. In a rigid body, it is the distance between 2 points inside the rigid body. R means what? This is the rigid body. The distance between 2 points is fixed. So if we take the origin here with respect to it, a fixed point Ri, distance is fixed. So inside a rigid body, what it is, the Ri is the radius vector, particle. Since Ri is a fixed vector related to the body, so its velocity dRi by dt in rotating body will be how much? Since Ri is fixed, it does not vary with time. So dRi by dt inside the body, rigid body, must be zero.
Hello, sir.
It is constant inside the body. This is with respect to external coordinate system. The Ri may be varying due to motion. Rigid body is moving or rotating. Position of this one with respect to this body is changing. This point may be due to rotation changing. But position of this body with respect to another point of rigid body is always fixed. So dRi by dt in rotating frame is 0. Rotating rigid body frame, rotating or rigid body frame is 0. So if you put 0 here, we found del R by del Ts, which is nothing but velocity, Vi is equal to omega cross Ri. Okay? You know V is equal to R cross omega, not first two. But here for a rigid body motion, when we substitute Vi, if the velocity measured from an outside observer, it must be equal to omega cross Ri. Okay? So now in place of this Vi, put omega cross Ri. Clear? Hello?
Yes, sir.
Uh, so, so equation look like this. But we know that A cross B cross C is equal to back minus cap B A dot C minus C A dot B. B means omega A dot C minus C A dot B. Ri dot Ri square and Ri dot omega. Ri dot omega means dot product component x component omega x plus y component omega y plus z component omega z. Okay, so this equation reduces this. A is equal to this. But R is equal to xi cap, xi cap plus yi cap plus zi k cap. Ri. R is equal to xi cap plus yj cap plus zi ith component. Xi cap, yi cap, zi cap. So omega also omega is I cap, omega is j cap, and omega is k cap. L is nothing but Lx I cap plus Ly j cap plus Lz k cap. Now compare the coefficient of I cap. Whatever I cap multiplied in x axis left hand side, it must be equal to the I multiplied term with I cap in the right hand side. So Lx must be equal to mi omega x Ri square minus xi all into this term. Isn't it? We write that. Okay. So Lx is equal to how much? mi omega x, because here vector is omega. First term vector is omega, its x component is omega x. So mi omega x. Here component is xi, x component. So xi whole into this xi square omega x plus xi y omega y, xi zi omega z. Okay, so I write taking omega x from common from these two terms, omega x mi ri square minus xi square minus, this is minus sign, mi xi yi and omega z mi xi zi. Okay, can you get equation 4 from equation 3? Hello?
Yes, sir.
Only component, x component lx, x component which is multiplied by I cap. In this omega put this one. So I cap only multiply omega x. So first term is omega x ri square. Okay? In here x component is xi. So put here xi into this. Hello? Clear?
Yes, sir.
Okay. Similar equation for all component Ly, Lz. Okay. So now I can write this. See, this is a something into omega x, something into omega y, something into omega z, and it has two. Suppose xi square, xi, here xi yi, xi zi. So I can write lead that xx component, xi y, xy component, xz component. So Lx can be written as Ixx plus omega x plus Ixy omega y plus Ixz omega z. Similarly, Ly and Lz. Okay. From this you can write Ly Lz comparing the coefficient. It can be write like this. Now what is the form of Ixx? Ixx is nothing but this one. Mi whole into Ri square minus Xi square. So Iyy mi whole into Ri square minus yi square. Izz mi into Ri square minus zi square. Okay. Then xx term, then xy term, yx term is how much? Xy term is this minus mi xi yi. Similarly, xz term is minus mi xi zi. Okay. Clear? Y, suppose I yz term. What will the I yz term? Hello, tell me. Hello.
minus m I
Huh.
y I z I.
Minus mi y z. This is the component. So it's the summation term. If you write in terms of integration, because for a continuous body, if a large number of particles stay inside it, summation is very difficult. We use integration, the continuous body. For integration, actually, this mass, integrated in terms of density, integration, charge density, into when we use integral from, we use density, mass density, mass per volume. So we use rho dV and integrate it, which actually give you mass. So when we convert it to integration, we actually use this rho dV in place of mass. So my expression will Ixx becomes integration of rho dV r square minus x square. Okay. Similarly, this becomes integration of rho dV xy. Combining these two, I can write like this: I j k, any component, whether j is equal to k or not, it will rho r square delta j k. Chronicle delta. If j is equal to k, then is term 1. Otherwise 0. If j is equal to k, it is 1. So it is r square minus x in xj x square. We get this form. When j is not equal to k, this will be 0. So we got this one product term. Okay, so general form is like this. Clear? Hello? Combine these two,
Yes,
I
sir.
write this equation. Okay. This is the general expression for any component of moment of inertia. Ijk. So actually in this term I can write L is equal to I omega, where I is actually 9 component, we call tensor, moment of inertia tensor. Because I can write this in matrix form. I has 9 component, Ixx, Ioxy, Ixz, Ioz, and it multiply to omega gives you L. Okay. So this I is known as moment of inertia tensor, which has 9 components. So L is called I omega. I is operator whose matrix element and the coefficient omega matrix. So M R square, you know that. And inertia tensor and the moment of inertia. The quantity I is identified as second rank tensor and is usually called the moment of inertia tensor or simply inertia tensor. That I, which has 9 component Ixx, Ixy, Ixz, Iyx, Iyy, Izx, Izzy, Izz, that is known as the second rank tensor and called moment of inertia tensor. Now go for the kinetic energy. What kinetic energy we know half mi vi square. Vi means vi vector or vi vector. But we know vi is equal to omega cross ri here equation 2. So putting here vi is equal to omega cross ri for 1 vi, then it will like this. Vi dot omega cross ri a dot b cross c. It may be equal to b dot c cross a and c dot a cross b. Slightly rearranging. B dot C cross A omega dot Ri cross B. I can write this. But why I write this? Because Ri cross I can take omega is a vector part. M is scalar to outside the summation because summation is over I. So I write like this. It is nothing but Mi Va is equal to Pi and Ri cross Pi is equal to L. So my equation becomes half omega dot L. Again, L is equal to I omega. Okay, so T can be written as half omega dot I dot omega. Okay? Or any problem? Have you get this equation or not?
Yes, sir.
Okay. Now look at here. Actually, we have a dot product is basically gives you a vector. Sorry, scalar. Cross product gives us a vector. Dot product gives us a scalar. Here, I dot omega means it is a scalar quantity. It cannot be just like simple behave as a vector and dot product to omega. So these type of things, okay, uh, can be simplified. Actually, these are called dyadics. Previously, it was known as dyadics. Now, this term is not used, but three vectors are written with dot products called dyadics terms. Okay. But simply we can, so I is not written here like a vector. It's a product, you can assume not dot product, you assume because I is not behave as a vector here. It is tensorial part. Okay. If you assume that omega is equal to as a magnitude omega and vector n cap, then this equation reduced will be half in place of omega, we can write omega n cap. So here also another omega. So multiply omega square n cap dot I dot n cap. This quantity is scalar which is known as moment of inertia. Okay. N I n cap. It can be written as a small scalar I. So it becomes kinetic energy half I omega square. And that I scalar is defined by n cap or in explicit form this term. Mi Ri square Ri minus n square known as moment of inertia about the axis of rotation. The scalar I n dot I dot n is known as moment of inertia about the axis of rotation. Okay, putting this we can write L is equal to omega plus Ri. Putting this you got this formula. But up to this very important and I come scalar. Okay. And this is general formula you know parallel axis theorem when you calculate moment of inertia half mi summed over I mi Ri square. Okay. Then we use for if there is a parallel axis, then it will be moment of inertia plus m r square m and distance of perpendicular distance of separation between them. Okay. This we already proved. Then we go for moment of inertia particularly. Okay. So we already write that I is equal to nin, if we assume n vector is given alpha I cap plus beta j cap plus gamma j cap, alpha beta are coefficients, then what will be its value? Then I dot n is equal to this I excess alpha. Again it will dot with n, so we got ixx alpha square plus iy beta square, izz gamma square plus 2ixy alpha beta, 2iyz beta gamma, and 2izx gamma alpha. Problem sometimes asks n is a given, vector is given, calculate the moment of inertia, matrix will be given. So component wise you multiply and solve by using this formula. Okay, this is important. Using this I, you can also define a vector rho. Rho is equal to n by root I. So that is rho square, it will be n square by I, n square 1 by I. So if you putting this, you can reduce this formula. Okay, is that here important is the moment of inertia of a solid sphere of radius r and mass m axis passing through the center is 2 by 5 mr square. You know that. And parallel axis theorem you also know in your plus 2. Suppose two axis everybody it is rotating about an axis here. If there axis some parallel axis here, what is the this is A, this is B, then what is the moment of inertia about this axis B? If its parallel distance, perpendicular distance is r, capital R. So you generally write I B is equal to IA plus MR square. Is not it? You know it are plus to MR square. If it is a perpendicular distance means suppose it's not in the straight line, then perpendicular distance means this one. R cross N. Actually M R cross N cap. Mod square. Perpendicular distance. Is not it? Hello?
Yes, sir.
You know it plus two. Then this problem is very important. Calculate the elements of the moment of inertia tensor for a homogeneous cube of mass m, density rho and side a, assuming that the axis lies along its edges with the origin at one corner. Okay. Using the formula what I derived for ij, you can calculate the moment of inertia in the object. Here a very important question. Most of the time this question asks, find the moment of inertia of a cube. So mass m, density rho is given and side array. Axis lies along the edge. Like figure axis is at one edge. Okay. All axis or origin at one corner of axis. So all are A. So how you calculate? Each side is A. So we have to calculate using this formula. Ijk is equal to integration over rho r squared is LV. Okay. This r square actually we know x square plus y square z square. Component wise or x1 square plus x2 square plus x square. What is xx component? According to our formula, xx component it will be 1 and j will be x, xk will be x. So r square minus x square. But r square is equal to x square plus y square plus z square. So r square minus x square will be how much? R square minus x square is equal to?
0.
No. R square minus x square is equal to how much? 0. Y square plus z square. R square minus x
No,
square.
sir.
Y square plus z square. So I can write this y square plus z square. But the dv means integration over 3x dx dy dz. Now integrate it. Limit is 0 to a. Okay. Actually there is no x here. So x separately integrate give you a. yz. First integrate with dy then z. Integrate y. It will be y cube by 3. Z square is z square y. Put limit 0 to a, 0 to a, so it is a q a z square. Again multiply with respect to z, integrate with respect to z. So it will be a z q by 3. So it will be 2 by 3 a to the power 5. Or if you, in place of density, use mass per volume term, m by a cube, volume of a cube, it will be 2 by 3 m square. And I y will be that much, I z, since it is a cube, symmetric along all axes, so all have same value. Okay?
Yes, sir.
Now off diagonal elements Ixy. How much from this formula Ixy? Tell me. I want to know about Ixy from this formula. Delta J if J is X, K is equal to Y, delta J K is equal to, if J is X, K is equal to Y, that means J is not K, then delta J K is equal to how much? The chronic or delta.
X.
What it means? Delta J K means what? It will be 1 if I is equal to J. Means same. Is equal to 0 otherwise.
I is
I
not.
is not equal to J. So tell me, my J is Y, K is Z. So delta YZ is equal to how much?
0.
0. So only rho r minus y. This one is y z. So yz component. Suppose xy component means it is xy xy. So my xy component first calculate. So it will be rho xy dx dy dz. Again there is no z. Integrate it first. So it gives you rho a, and integrate this xy dx dy with respect to x means x square by 2. Put a square by 2 y dy. Again integrate it y square by 2. Put a 5 by minus 4. So minus 1 by 4 ma square, putting the volume. Okay, this since it's a cube, so I yz is same, I xz is same, I zx is same, and the symmetric also components. So I got this matrix. Okay,
Yes, sir.
hello. This is one of the important questions sometimes asked in examination. Okay. This was a simple problem. N is given, matrix is given. You have to calculate the moment of in the tensor using the formula what I written here. This formula. Okay, you have to do it. N is given. So this component means alpha. This is alpha as per our formula. This is beta. This is gamma. X component, Y component, Z component, N vector. Because I take here N is equal to alpha I cap, beta J cap, gamma K cap. So my formula is this. Using this you can calculate. Okay. No problem. Then next one is torque free motion. Ah. Torque free motion of rigid body. Sorry, not Euler equation. Then solving rigid body problem and the Euler equation of motion. Okay. So actually in rigid body we have see this two kind of kinetic energy, rotational kinetic energy and translational kinetic energy, half mv square plus half I omega square. So we have to consider rotation inside it. So we follow the Lagrangian formulation, means we get the Lagrangian TV, but it is very difficult to solve in that way. We follow the Euler's equation of motion, one procedure to solving the rigid body problem. Okay, so this is the introduction part. Come to directly Euler equation of motion. For the rotational motion about a fixed point or the center of mass, if the fixed point is not given, the center of mass, the direct Newtonian approach, all Newton equation, F is equal to ma, tau is equal to dl by dt. Okay, these equations. Newton leads to a set of equations known as Euler equations of motion. We consider either an inertial frame whose origin at the fixed point of the rigid body or a system of space axis to origin at the center of mass. We have two options. Either we consider a rigid body whose origin is a Origin of body set of axis is a fixed point. This one is fixed. If fixed point is not given, then we assume this will be center of mass with space at origin and the center of mass. So decisions are same. Leave that. From Newtonian mechanics, we know that if torque n, here I take symbol n, torque is equal to dl by dt. Torque, outside torque is dl by dt with respect to space coordinate. This formula is valid for space coordinate. Now, how it relates to the rotating coordinate? Actually, whatever formula we study, all for space, normal. Uh, but we are inside the earth is rotating. We are assuming that that formula is existing for also us. But actually, since the earth is rotating, all moving phenomena are affected because there is some kind of change due to rotation. Because dl by dt s is equal to dl by dt v, means inside earth or inside the rigid body, plus omega cross L due to rotation. So it appears, since we are in earth, dl by dt v is equal to dl by dt s minus omega cross L. Okay, we know that. Now we have to solve this equation. We know this is the equation. So in dl by dt is n, so put here n. So n is equal to dl by dt v plus omega cross L. V means inside earth. So we can remove the subscript and write dl by dt plus omega cross L is equal to n. But L is equal to I omega. If I1, I2 is the principal moment of inertia. Here we principal moment of inertia means if the moment of inertia tensor is diagonalized, then all diagonal elements are known as principal moment of inertia. Diagonal elements are called principal moments of inertia. Diagonal elements. So it is simple L is equal to I omega, only simple multiplication. Okay. If you diagonalize the moment of inertia matrix, then the diagonal elements. So I1 omega 1 I cap plus I2 omega 2 I3 plus, okay. Now L is this. What is dl by dt? So the omega 1 component, omega 2 component, omega 3 component along x axis, y axis, z axis component angular velocity. It may vary. So we can write, but principal moment of inertia is fixed. So I1 omega 1 dot plus I2 omega 2 dot plus I3 omega 3 dot. Okay. So n is equal to, using the formula, it is dl by dt, it is omega cross L, the cross product. Okay, can you get this equation? Hello?
Yes, sir.
Yes, sir.
So if you take its determinant I cap into this, j cap, k cap, we got this. Now compare the coefficient of I cap, j cap and k cap separately. Whatever multiplies I cap, you see left hand side n1, right hand side I1 omega 1 dot and this term. Okay. Similarly for n2 j cap, I2 omega 2 dot and this term. Okay. Plus k cap, I3 omega 3 dot and this term. So compare you get this. These equations are known as Euler equations of motion. If one line you can write it ni. I means 1, 2, 3, whatever may be. It will be if 1 dot. So I di by dt. Here if 1 is absent. So epsilon ijk omega k ik. The order is, it means if epsilon ijk means if any two indices are same, then it will be 0. If I is equal to j, then it is equal to 0. If j is equal to k, then it is equal to 0. If in the order even permutation, I think I already discussed that. If in a even permutation for 1, 2, 3, order is same. This clockwise, then it is +1. If odd permutation, then -1. For this one, you can write only these three represent the Euler equation of motion of a rigid body with 1 point fixed. Okay. For a heavy symmetrical top, the next topic, we actually take symmetrical means is I1 is equal to I2 but not equal to I3. symmetric about the third z axis. So I1 is equal to I3. Okay. Now another thing is torque free motion of a rigid body. If torque is zero, if the N1 0, N2 0, N3 0, if total torque is zero, N1 0, N2 0, N3 0. So what it means? I1 I2 plus this is zero. Not it. Torque free motion I1 I2 take it one side, then it will become like this. Is not it?
Yes,
Zero.
sir.
So you take one side, so it will become like this. Torque free motion of a rigid body. But if you add this, you see, suppose you add omega 1 in equation 1, so omega 1 left side, omega right side, omega 2 in equation 2, omega 2 left side, omega 2 right side, omega 3 in equation 3, and omega 3, and r. What will be the result? Can you say what will be the right hand side? All are omega 1, omega 2, omega 3. See, all are same. If I take common, then it will be I2 minus I3 plus I3, 0. I1 plus I1, 0. I2 minus I2. So result will be 0. Isn't it? Hello?
Yes, sir.
Yes, sir.
So that will be 0. But what left hand side? I1 omega 1 omega 1 dot. If C, actually it is derivative of kinetic energy. Uh, okay. Will be 0. So left hand side is actually derivative of this term, kinetic energy 0. So kinetic energy is constant. Again, torque is 0. Torque 0 means dl by dt 0. So L is also constant. For torque free motion of a rigid body, angular momentum and kinetic energy are constant of motion. Sometimes I show that for a torque free motion of rigid body, angular momentum and kinetic energy are constants of motion. Okay? These things are not needed. Leave that. Then important thing is symmetrical top. Heavy symmetrical top with 1 point fix. Basically, its example is some gyroscopic instrument and simply your child stop, not to what you play. Okay. So if you look this motion of this top, how it rotates, you see it moves just like suppose this one is it tilted motion. If you leave in the floor, it will move just like tilt motion about this axis. One time motion. Another it is rotating itself. And this motion you are seeing about this axis. Isn't it? Second thing, third thing is you say sometimes this vibrate. If you leave it on the floor, it will vibrate motion about that axis. So there are three kind of motions are available. Okay. Consider the motion of a symmetrical body. It is symmetric about the z axis, symmetric about z axis. So we take I1 is equal to I2 is not equal to I3. Okay. Consider the motion of a symmetric body in uniform gravitational with 1 point on the symmetry axis is fixed in space. A wide variety of physical systems ranging from child stop to complete gyroscopic instruments are example. Both for its practical application and many of the illustration of many of techniques previously developed, the motion of heavy symmetrical top deserves a detailed exposure. The symmetry axis is of course the principal axis and always chosen in the z axis. Since one point is stationary, the configuration of the top is completely specified by three Euler angles. 1 point fixed means only 3 degree of freedom, 3 Euler angles, theta, phi and psi. Okay. Theta give the inclination of the z axis from the vertical. This angle is theta. This top is about this vertical. Phi measures the azimuth of the top about the vertical and psi is the rotation angle of the top. Okay. So psi, if you compare about this Actually, this is second angle theta. Okay, phi this angle and this psi. Phi theta psi. Phi motion phi is actually rotation about z axis. Phi first one, which is called azimuth of the top. Then theta, then psi. Psi is last rotation about z1 axis, or you can say z prime axis, final axis, body axis. So in this figure, these are the phi theta psi. If you compare last class, these are the phi theta and psi angles. Is not it? Hello?
Yes,
Hello?
sir.
So three motions. Similarly, psi dot is rotation of the top about the own figure like z. Psi is rotation around this axis. Body z axis. Now here is body. Last rotation is about body z axis. So psi is actually rotation about this axis. So psi dot means its variation, rotation of the top about its own figure axis. Figure axis means shown in the figure. What axis? Then phi dot. Phi dot precise rotation of the figure axis about the vertical axis. Theta dot, that is theta dot rotation. Phi theta slightly sorry. This is theta dot. This is phi dot. Wrong. Theta dot is precession or rotation of the figure axis about vertical axis. This it is like this, which called precession. This whole top is executing a motion around this vertical. If you see, the top is moving like this. That is called motion is called precession. And phi dot nutation bobbing up and down figure z related to the vertical. The psi, actually this is the motion of this a vertical straight, then its figure axis may slightly bobbing up and down motion with angle psi. That motion is known as actually nutation. Three motions: rotation, precession, nutation. Rotation is that top is rotating about this axis. It is called rotation. Also, if the vertical, this top is rotating like this. Next one here, around this axis, it is execute a motion. That is known as precession. Sometimes this this point or axis, it may moves up and down rightly. That is known as nutation or bobbing up and down. Clear? Hello?
Yes, sir.
Hmm. For every symmetrical term, actually this is the condition. Now we know that if putting in the Euler equation motion, if put I1 is equal to I2, then one equation cancel, which is I1 minus I2 term. In this term, actually there is a I1 minus I2. Since I1 is equal to I2, this becomes 0. So third term was only I3 omega 3 term. This is the Euler equation, we get this. Okay, so but Euler equation may not provide most useful description of the motion of symmetrical top. So we use Lagrange's procedure. Lagrange's procedure means we need kinetic energy and potential energy, then we get set the Lagrangian. Kinetic energy of heavy symmetrical top will be half I1 omega 1 square plus half I2 omega 2 square plus half I3 omega 3 square. Since I1 is equal to I2, I write like this. But we know that components of angular velocity vector along body set of axes, actually you have to remember if derivation acts. This is a relation between angular velocity and this component phi theta psi. If want you can derive it, but it is very lengthy. So you have to remember this if the derivation asked in your examination, because it is a very important question for our students. But I don't know whether they are asking long question or not. So omega 1 is related with phi psi theta psi like this. Omega 2 and omega 3 this angular velocity. Substituting these three, you can get like this. Okay, a substitution. Then slightly rearranging. We got T is equal to half I1 this. Right. What simplifying, we get this. It is a simplification, no? Square all these things are written there. It is kinetic energy, but the potential energy, but in the gravitational field, the potential energy is solved already. It's the potential energy. mgh, what mg, and the vertical distance. Okay. And the distance is how much? This distance, this angle is theta. So this vertical distance is how much? Hello? This is L. This angle is theta, just like a figure. This is L. This angle is theta. This one is 90 degree. So what is this? This side will be how much? Hello? This side will be how much? L cos theta. Theta L. So L cos theta. The side which touches the angle theta is L cos theta. Opposite side, this one is L sin theta. Is not it? Hello?
Yes, sir.
So L cos theta. So potential energy, we can write actually mg into L cos theta. So Lagrangian kinetic energy minus potential energy from this equation. From here, you see which are cyclic coordinate does not appear in the Lagrangian. Tell me, this is the Lagrangian. Which are cyclic coordinates? Cyclic means does not appear in the Lagrangian. Among theta, phi, psi, is there any cyclic coordinate? That means phi, theta, psi does not appear any cyclic coordinate. Hello?
Yes, sir.
Which one is the cyclic coordinate? Theta is present in the Lagrangian? Yes or no? Theta is present or not? Theta is present?
Yes, sir.
Phi is present? Tell me whether phi is
Yes, sir.
present. Where is phi? Is phi dot? Phi
Phi
dot.
dot, phi dot,
Uh,
phi dot, phi
no
dot.
phi. So phi is a cyclic coordinate. Similarly, psi, no psi. So psi is a cyclic coordinate. The corresponding momentum of cyclic coordinate are constant. We know that. So p psi del L by del psi is a constant. Well, let's take it as I1. And p phi del L by del phi dot is another constant. Okay. We write it as I1b. So there are two constant p psi and p phi motion expressed there. So in terms of A and B, we write like this, I1A into I1B. So now a total energy, or you can say Hamiltonian can be written as T plus V, Hamiltonian or energy, total energy. So half kinetic energy plus potential energy. If Lagrangian also does not contain time, so E is also a conserved quantity. We know if time is cyclic, then E is a constant. Only three additional quadrats are needed to solve the problem, and they easily obtained from the first integral. There are three constants. We need more three constants. That can be achieved from this equation 5. Look, the p size I1A. So I3 side out from there we get this. And using it in equation 6, only simplifications. Okay, I3 side out in place. We get this equation. And finally we found I dot is equal to b minus a cos theta by sin square theta. If theta are known as a function of time, then equation 9 could be integrated to furnish the dependence of phi on time. If you integrate it, then d phi by dt integrated to phi. So dt, but if you know phi will how much? Phi will be integration of this. But for that we have b are constant. We have to know the variation of theta with time. How if theta is a function of time, then if you know that you can get this. Similarly, from that equation, we found psi dot is equal to this. If theta is known, you can also find the psi dot. And from 9 and 10, these equations are used to eliminate phi dot and psi dot from the energy equation using this equation, or in place of phi dot putting this and psi dot putting this in E equation, you can remove phi dot psi dot from here. It is only theta dot. Holding the differential equation theta only. So the equation will be only in theta, derivative of theta and theta. How this will be? If you see, use this omega 3 from equation 5, so energy will be E minus I3 omega 3 square. E is a constant of motion, so E minus another constant of motion is also a constant of motion, E prime. Now let's do our total energy is this one, T plus B. Put in place of phi dot its value, psi dot its value. So now it is on some theta and theta dot mgl cos theta. If you simplify this, actually these two terms cancel. So only this one term exists of I3 I1 A by I3. But I1 is equal to I3 omega 3. You can put this. So it is I3 omega 3 square mgl cos theta. So E minus I3 omega 3 square by 2, to take this side, will be this I1 square plus mgl cos theta, which is or E prime. It is another constant. So this is a constant of motion. So above equation 12 has the form of equivalent one-dimensional problem in the value theta. So it is just like a equivalent one-dimensional problem because it is kinetic energy, rotational kinetic energy. If you are this term with potential energy, okay, then it behaves like a effective potential energy, E plus V prime. Okay. So effective potential energy is like this. I already did some problem in your central force motion equation of orbit, nature of orbit calculation. So now this equation just like a effective potential and effective energy. Thus we have now many constants we can define. We have a constant E minus I3 omega over 2. We can set it alpha, right? Taking LCM, 2E minus I3 omega 3 square by 2. So 2 is a constant, divide leave that 2E minus I3 omega 3 square. But I1 alpha is equal to this. So alpha is equal to this one, is a constant. Similarly, beta 2 mgl by I1, we divide I1 with all other constant terms. Mgl is a constant, so divide I1 with it. 2 mgl I1. That is P psi is a constant, P psi I1. P phi for I1. To normalize it, actually normalize constant. These are called normalized constants. Okay. Divide I1 is term constant. In those and substituting the alpha beta AB, we found in terms of alpha beta IB our equation. Is this, substitute these things, alpha beta AB, we find out alpha is equal to theta dot square plus B minus A cos theta square by sin square theta plus beta cos theta. If we again take LCM and simplify, you got this. Now put, for solving it, put u is equal to cos theta. If u is equal to cos theta, then u dot du by dt minus sin theta d theta by dt or sin theta dot. So substitute here. So sin theta dot square means it will be u dot square. Okay. Sin square theta 1 minus cos square theta is equal to sin square theta 1 minus u square. Alpha minus beta cos theta, alpha minus beta u. B minus A cos theta, B minus A u square. Okay, are you getting my point?
Yes, sir.
You get this equation. Actually, this equation gives the solution, a basic idea about the motion of symmetric tau. U dot square this, so u dot is root over of that quantity. So u dot du by dt, so like this, dt is equal to du by this. T is equal to, if you integrate it, but that is square root term. If for general motion, we have to consider the square root term. With if you multiply here, what is inside the square root? Okay, leave that, or this term. If you multiply, you find 1 is beta uq, is highest power of u is q, when beta u multiplied with u square. So we actually found, got by multiplying, we given here this term by multiplying at beta uq minus alpha plus a, here a square u square, here alpha u square, alpha plus a square u square, again 2ab minus beta u, here beta u, when multiple with 1, here 2ab u, 2a minus beta u, another constant is b square and alpha. Alpha minus b square is a constant. So there is an equation like this: x cube plus x square something ax cube plus bx square plus cx plus d is equal to 0. Equation right hand side. Okay. So for a gyroscope, the center of mass is the fixed point. So beta is equal to 0. For a gyroscope, beta is equal to mgl, the center of mass is the fixed point. So L is 0. So gyroscope beta is equal to 0. It is a quadratic equation, easy to solve. Quadratic beta 0, top or going to be. But other things you see, to understand the general motion of spin wheel, we have to consider only the cases where beta greater than 0. Okay. If beta is than 0, then it will be negative. But whether u is positive, and then it will be negative. So for general motion, we have to assume that beta greater than 0. So the roots of the cubic polynomial of angle theta are the sine, a turning angle theta. Knowing these angles will give qualitative information about the motion. From this, we have to know the turning angles, because how you know turning angles? Examine this function. If this function has both positive and negative value, then there must be a point where it crosses the axis 0. That is called turning. Knowing three angles with qualitative picture, there are, since it is a cubic equation, u to the power q, there are three roots of the equation. There are three roots of the cubic equation and three possible combination of solution. There can be one real root and a complex conjugate pair of roots. There can be three real roots, two of which are equal, and there can be three real and unequal roots. What are the possibility? Maybe three are real, three are real, two are equal, one real, two are complex. Okay. This possibility depend on the relative signs of the magnitude of the four constants alpha, beta, a, b. There is also the physical constant that solution u must satisfy -1 to +1. So u is basically cos theta. You know cos theta limit is -1 is less than equal to cos theta is less than equal to +1. Since we are taking u is equal to cos theta, so u will satisfy that equation. U value is only between -1 to +1. Okay. So we'll draw all the figures if u greater than 0, which would be case if the top is supported by a surface. Okay. Now for u large, the dominant term is a beta uq. If u is a large one, very large, then this will be dominant. Uq is very large. It's always, since beta is always positive, so beta uq is always positive. If u is positive for large, positive u. So if u is large, function is positive. And negative for large, negative u. If u is negative, then function is negative. If u is positive, large positive, then it is positive. If large negative, then it is negative. This term is dominant, other are neglected in comparison this. So that means there must be a transition 0. Positive negative means there must be a transition 0. Okay. At point u is equal to ±1, if u becomes equal to minus v by l whole square. If you take u is equal to ±1, so what will happen? U square 1, 1, here also 1. So beta minus alpha plus a square plus 2ab minus beta plus a minus b square. Minus beta, beta cancel, minus alpha, alpha cancel. So it is basically a minus b whole square. If you put -1, actually that is minus beta minus cancel. Same thing. So, here minus a square, it will become plus a square. So actually minus a square if u is equal to plus 1, now beta cancel, it is minus a square minus b square 2ab, taking minus common, a square plus b square plus 2ab, minus 2, a minus b the whole square. If u is equal to minus 1, then it will be minus it. So there is a minus sign here. So we can say it will be minus a square minus b square minus 2ab, taking minus common, a plus b the whole square. Okay? Is not it? Hello?
Sir.
Yes,
Yes.
sir.
So there are two roots, whatever, a minus b or a plus b square. So this becomes minus b minus a whole square, b plus a square. And therefore always negative except the unusual case where u is plus 1, plus minus 1 is a root. If u is a plus minus 1 root, then not happen. So there may be transition. Look, for any actual of f you will have two roots u1 and u2 between minus 1 and plus 1 because u is equal to cos theta. Okay. Cos theta maximum value plus 1, minimum value minus 1. So minimum two roots exist because if you see the cos theta figure, this like what is given here. Okay, there are at least two time roots are present here. Let's go neatly. These are given the roots. And the top moves such that cos theta always remains between these two roots. The location of these roots and behavior of phi dot psi dot for theta provide much qualitative information about the motion of the top. Okay, these are the details if you want to study this. The actual motion is given here. You have to derive this and give this completely. Okay, this is about rigid body. But we have something to discuss what we left. Two things: Liouville's theorem, um, then for relativistic particles bilinear covariant. Okay, so one two classes I will take.
Yes,
Okay,
sir.
most part of our syllabus is covered, but there are only few things what we left. Part we take as per my assignment. I have to take two classes more. Okay.
Okay.
Mm. If possible, I will take a Saturday or Sunday because tomorrow you have two classes, isn't it? Uh, so I'll tell you if I take either Saturday or Sunday. Okay?
Yes, sir.
Okay, sir.
Okay.
ସାର୍ ଆପଣଙ୍କ କ୍ଲାସ୍ 13-14 ବେଳକୁ ବି ଅଛି ଟାଇମ୍ ଟେବୁଲରେ।
ଅଛି 13, 14, 15 ମୁଁ ସେଯାଏ ଯିବାକୁ ସେ କହିଛନ୍ତି ଶୀଘ୍ର ସାରିଦେବା ପାଇଁ। ମୋର
ଆଜ୍ଞା
ଆଉ କ୍ଲାସ୍ ତ ସେଠି ଅଛି 13, 14, 15ରେ। ତା ଭିତରୁ ମୁଁ ଗୋଟେ କ୍ଲାସ୍ ନେଇଗଲି। ମୋର ମାନେ ଆର ପେପର ପାଇଁ 4ଟା କ୍ଲାସ୍, ଏଇ ପେପର ପାଇଁ 6ଟା କ୍ଲାସ୍, 10ଟା କ୍ଲାସ୍ ମୁଁ ନେଇ ସାରିଲିଣି। ମୋତେ 12ଟା କ୍ଲାସ୍ ଦିଆଯାଇଥିଲା। ଆଉ 2ଟା କ୍ଲାସ୍ ଅଛି। ମୁଁ ସେଟା ଦେଖୁଛି ଶନିବାର ରବିବାର ନେଇଗଲେ ମୋ ପାଠଟା ବି ସରିଯିବ। ଆଉ ମୁଁ କାହିଁ ଲାଷ୍ଟ ସେତେବେଳକୁ
ଆଜ୍ଞା
2ଟା ନେବି ଦିନ ପରେ ହେଲା। କାରଣ ଆମର ମେନ୍ ସବୁ କଭର ହେଇଯାଇଛି। ଆଉ ଖାଲି ଛୋଟ ମୋଟ କ'ଣ ଅଛି ମୁଁ ଦେଖିବି। ଆଉ ଦେଖିବା କ'ଣ।
ସାର୍ ଲାଷ୍ଟ କ୍ଲାସରେ କିନ୍ତୁ
ଲାଷ୍ଟ କ୍ଲାସରେ
ଇମ୍ପୋର୍ଟାଣ୍ଟ
ଦେଖିବା
କ୍ୱେଶ୍ଚନ୍ ଦେବେ।
କୋଶ୍ଚିନ୍ କ'ଣ ଗୋଟେ ଆକ୍ଚୁଆଲି ଇମ୍ପୋର୍ଟାଣ୍ଟ କୋଶ୍ଚିନ୍ ଗୁଡ଼ା ପ୍ରୋବ୍ଲେମ ଟିକେ ପଡୁଛି ସବୁ। ତେଣୁ ସିନା ଲଙ୍ଗ
Sir,
କୋଶ୍ଚିନ୍ ବୋଲେ ଆମେ ସିନା କ'ଣ ଦେବୁ ସିଲେକ୍ସନ ଦେ ଏଇଟା ପଢନି ଏଇଟା ପଢିବ
ସାର୍
ତମେ ପଢିବ।
ପ୍ରୋବ୍ଲେମେଟିକ୍ ବି ପଡୁଛି
yes, sir.
ସବୁ
ଆପଣ
ଲଙ୍ଗ
ପାର୍ଟ କହିଦେବେ
କ୍ୱେଶ୍ଚନ୍।
କୋଉ ପାର୍ଟଟା ଇମ୍ପୋର୍ଟାଣ୍ଟ ପାର୍ଟଟା।
ଆଉ ସେ ତେଣୁ ସେ ଲଙ୍ଗ କୋଶ୍ଚିନ୍ ତ ତମର ବୋଧେ ପଡୁନି ଲାଷ୍ଟ କୋଶ୍ଚିନ୍ ଯାହା ମତେ ପଠେଇଥିଲ ତା ଦେହରେ ତ ସେ ସବୁ ପ୍ରୋବ୍ଲେମ ପକେଇଛନ୍ତି ଭେରି
ହଁ ସାର୍
ଡିଫିକଲ୍ଟ
କୋଉ
ମାନେ।
ସାର୍ ସବୁ ଲଙ୍ଗ
ସାର୍
କ୍ୱେଶ୍ଚନ୍
କୋଉ
ପଡୁଛି।
ଚାପ୍ଟରଟା ନହେଲେ ଇମ୍ପୋର୍ଟାଣ୍ଟ ସେଇଟା କହିଦେବେ ନହେଲେ।
ହଁ ଦେଖିବା ମୁଁ ଦେଖି ସେ କୋଶ୍ଚିନ୍ ଟା ଷ୍ଟଡି କରି ତାପରେ ତମକୁ କହିବି ଆଉ ହେଲା।
ହଁ ହଉ ସାର୍। ହଁ
ହୁଁ।
ସାର୍।
ଆଉ ମୁଁ ଜଣେଇବି ଯେ ଶନିବାର ନେବି ସେଦିନ ଲେଖିବି ତମକୁ ଆଉ ହେଲା। ନହେଲେ ସଣ୍ଡେ
Yes,
ଦିନ
sir.
ନେବି। ହଁ ଓକେ ତାହେଲେ ମୁଁ ରହୁଛି।
ଆଜ୍ଞା ସାର୍। ଆଜ୍ଞା ସାର୍।